Hello everyone, my name is Oscar Venegas and this is the presentation for the laboratory number 4, comparing GNN aggregation methods on the PubMed dataset. So my presentation is about comparing different aggregation methods in graph neural networks using PubMed dataset. The goal of this lab was to understand how the aggregation step affects node classification performance, runtime, and overall mobile behavior. I first compared several base GNN models, then performed a control ablation on aggregation methods, and finally extended the lab with a recent paper-based method, PNA. Let's start. So before comparing models, it is important to understand what aggregation method means in a GNN. In a message passing graph neural network, each node updates its representation by gathering information from its neighboring nodes. The equations shown in the slide shows this update process, where the new presentation of a node depends on its previous representation and on an aggregation summary of the features coming from its neighbors. The aggregation function is the rule used to combine those neighbor messages into a single summary. Different aggregation methods preserve different types of information, so design choice can affect both model accuracy and computational cost. So for this lab, I use, as I mentioned, PubMed citation network dataset for a node classification task. In this graph, each node represents a scientific paper and the H's represent citation relationship between papers. The dataset contains 19,717 nodes and 88,000, about 90,000 H's, 500 node features, and 3 output classes. For the experiments, I use Python in Google Colab with PyTorch and PyTorch Geometric, along with NumPy and Pandas for dataset handling and results organization. To keep the comparison fair, I use the same general training setup across experiments, including a hidden dimension of 64, dropout of 0.5, and the Adam optimizers. Finally, 200 training epochs. That's basically my dataset and experimental setup. So baseline model architecture. This slide shows the baseline model comparison results. Among all 4 models, GCN performed the best on the test set, reaching an accuracy of 0.78, almost 0.79. And it was also a fastest model to train. GraphSage with mean aggregation had the best validation accuracy, but that did not translate into the best test accuracy. GAT was interesting because, although it was a more flexible attention-based aggregation mechanism, it was by far the most expensive in runtime and still did not outperform GCN. GIN also performed reasonably well, but again, it did not surpass GCN, in this experiment at least. So the main takeaway from part 1 is that the simplest model in the comparison ended up giving the best trade-off performance, accuracy, and efficiency. So aggregation ablation, the GraphSage, GraphSage. After comparing different baseline models, I wanted to isolate the effect of aggregation more directly. So in part 2, I used the same GraphSage model and kept the rest of the setup constant, including the dataset, the split, the hidden size, the optimizer, and the number of training epochs. The only thing I changed was the aggregation rule. I evaluated mean, sum, and max aggregation to see how much this choice alone changes the final result. This is useful because it gave me a clearer comparison than changing the full model architecture. So the model performance and graph representation. This slide shows the result of the control ablation using graph Sage. The main observation is that changing only the aggregation function led to measurable differences in performance. Some aggregation reduced the best test accuracy, while max produced the highest validation accuracy. Mean was also competitive and remained close to the other two, although the differences were not dramatic. They are still important because they show that aggregation is not just a small implementation detail. Even within the same architecture, the choice of how neighbor information is combined can affect both generalization and efficiency. So for the part 3, as it was asked, the principal neighborhood aggregation, or PNM. For the paper extension, I chose PNA because it fits very naturally with the theme of this lab. In the earlier parts, I compared single aggregation strategies one at a time, such as mean, sum, or max. PNA takes a different approach. Instead of choosing just one, it combines multiple aggregation statistics together. In my implementation, I used mean, max, and standard deviation along with degree-based scalars. The motivation is that different statistics capture different aspects of the node's neighborhood. So combining them can provide a more informative representation than any single aggregation alone. So after implementing the PNA, I compare it against the baseline models from part A. PNA reached a validation accuracy of 0.786, almost 0.79, and the test accuracy of almost 0.78. So it remained in a reasonable range, but it still did not exceed the performance of GCN, which had the highest test accuracy overall. The biggest difference was the computational cost. PNA required about 323 seconds to run, which was dramatically slower than the other models. This suggests that, at least for the PubMed dataset and this setup, the added complexity of combining multiple aggregators did not translate into better overall performance. It did, however, clearly demonstrate the trade-off between expressiveness and efficiency. So, to conclude, the main lesson from this lab is that aggregation has a direct impact on both predictive performance and computational costs in GNNs. On the PubMed dataset, GCN ended up giving the best trade-off since it achieved the highest test accuracy and also had the shortest time. The graph Sage ablation showed that even when the architecture stays fixed, changing the aggregation rule still changes the outcome. Regarding the part 3, the part 3 extension with PNA was useful because it showed that the other side of the trade-off, a richer, more expressive aggregation mechanism, can come with a very large computational cost. So, overall, this experiment suggests that the best aggregation method depends not only on expressiveness, but also on efficiency and the specific dataset. So that was my presentation for the laboratory number 4. Thank you so much, and this is the last slide with the references that I used. Thank you so much.